So step two is to set the criteria for deciding whether you should accept or reject the null hypothesis. And I just want to leave a disclaimer here that I'm simplifying steps two and steps four a lot. I'm not introducing concepts like standard error of the mean or z-scores. I just want to give you conceptually what's happening. If you want a deeper understanding, we can talk about that another time, or I can give you some resources on that. But I don't want to make it more complicated than it already is. So I'm leaving out some information, but the basic concept is still here. All right, so we need to figure out whether to accept or reject the null hypothesis. And in order to do this, we need to determine what the expected mean for our sample would be if the null is true, right? And fortunately for our example, I set it up so that we know already what the expected mean would be. The expected mean would be 100 because IQ tests are standardized to have a mean of 100. But oftentimes you don't know what the expected mean is, and that complicates things a little bit, and we'll get to that in a minute. But what you're trying to understand is how far does our sample mean have to be from the expected mean, right? So if our sample mean is relatively close to the expected mean, then that would provide support for the null hypothesis. Whereas if our sample mean is very far from the expected mean, that would suggest that the null hypothesis is not accurate and we can reject the null hypothesis, which would then in turn mean that we could accept the alternative hypothesis. So the way hypothesis testing is set up is that there's only two outcomes. The data can either support the null hypothesis or it can support the alternative hypothesis. It cannot support both. So it basically is designed to be where it supports one hypothesis or the other. So it's helpful in that sense, in that if it's far enough away, you can reject the null hypothesis, which then means you can accept the alternative hypothesis. Now, to fully understand how far a sample mean has to be from the expected mean, you have to have a basic understanding of normal distributions. And I'm assuming you learned this in stats class, but in case you didn't, I'm going to give you a very quick refresher, right? So a normal distribution would look like this, and it has three important characteristics. And this is something that you should know for the exam. First is that the mean, the median, the mode, so those are your measures of central tendency, they are all the same. Second, the shape is symmetrical around your mean, median, and mode. And then finally, the tail of the distribution approach but never touch the x-axis. So if you need to visualize it, if you forget on an exam and I ask you what are the three characteristics of a normal distribution, you could draw the distribution and then you put these numbers here to help you figure out the answer. So 1 means that the mean, median, and mode are all the same. 2, the scores are symmetrical around the mean, median, and mode. And then 3, the tails of the distribution, right, as they get further away from the mean, median, and mode, approach but never actually touch that x-axis. So what that indicates is that any outcome is theoretically possible, but probably very, very unlikely to occur. What you also need to understand is that if you have a normal distribution of scores, then you can make some, you can have an understanding of how those scores are distributed in that distribution. And with normally distributed probability scores, what you'll know is that 68% of your scores are going to fall within one standard deviation above and below the mean. 95% are going to fall within two standard deviations above and below the mean. And then 99% are going to fall between three standard deviations above and below the mean. So now you have a sense of the probability of getting any given score in that distribution because it's normally distributed. Now, if your distribution is very skewed, then these percentages don't necessarily hold up anymore. So again, I'm more of a visual person, so I'm going to visualize it for you. So what you see here is the area in red. That's the area of one standard deviation above and below. So 68% of your scores are going to fall within that range. 95 are going to fall between two standard deviations. So that's the green area plus the red area. That's 95% of the scores in that distribution. And then 99% are going to fall within three standard deviations. So that's the blue, the green, the red areas. That's all of that area is 99%. And then as you can see here, there's still like a half percent on either side of the distribution. So for our example, we already know that the expected mean is 100 because that's how it's been standardized. And again, normally you don't know the expected mean. So what we have to do, what a program would do, is it would calculate the distribution of sample means. So it would take all possible samples of 50, and it would run a simulation of all possible samples of 50 and give you a distribution. And that distribution of those samples of 50, if you graphed it, would be a normally distributed distribution of scores. And that way you would know the probability of getting any particular sample of 50, what the score could be. Because normally distributed, we know that 68% of those possible samples of 50 are going to fall between one standard deviation above and below the mean. 95% are going to fall within two standard deviations above and below the mean, and 99% are going to fall within three standard deviations above and below the mean. So because this distribution of all possible sample means is normally distributed, we have that information that we can use to our advantage. Now, if you want to kind of see how you can create this kind of distribution of sample means, you can try this simulation at home. Just go to this link here, and it'll give you some instructions. As you can see, as you add more samples, it'll start looking like a normal distribution of scores. It's kind of cool to do. It's not essential, but I think it might help you understand what a distribution of sample means is trying to do. All right, so let's go back to our example. Again, because we know that the mean is 100 and we have a standard deviation of 15 for IQ tests, now we know that 68% of our scores are going to fall between 85 and 115. 95% are going to fall between 70 and 130, and then 99% are going to fall between 55 and 145. Okay? So now let's go back to step 2. We need to set a criteria for deciding whether we should accept or reject the null hypothesis. And again, for our example here, we're trying to figure out how far our sample mean of 50 has to be from the expected mean of 100 before we can reject the null hypothesis. And it's important now for you to understand the concept of alpha level, also called significance level. For most studies, people tend to set their alpha level to be 0.05. And this is saying that in order to be able to reject the null hypothesis, their sample mean has to be in the top 5% of the distribution of all possible sample means. Anything that's greater than that 5%, so if it's 0.07 or 0.10, you would accept the null hypothesis or you would retain the null hypothesis. If it's below 0.05, so let's say it's 0.04 or 0.01 or 0.001, those are the contexts when you would reject the null hypothesis and conclude that you have a statistically significant result. If you want to be more conservative and have a more stringent alpha, you can set it to be 0.01. So that means you'd have to get a sample mean that's in the top 1% of all possible sample means before you can reject the null hypothesis. So here's a visualization of a one-tailed test. A one-tailed test is when you're making a specific prediction in terms of the direction of the effect. So our example, we're saying that the pill is going to have a positive effect on cognitive functioning. So that's considered a one-tailed test. A two-tailed test is when you're not making a direction, you're just saying that the results, your sample mean would be different from the expected mean. which means it could be higher than the sample mean, the expected mean, or it could be lower than the expected mean. It's just different. And typically, researchers want to be more precise, so they tend to make one-tailed tests. In this example, again, we're saying that the pill will lead to improved cognitive performance. As a result, if alpha is 0.05, we can conclude that we're going to need a sample mean that's going to have to fall more than just around 2 standard deviations above the expected mean before we can reject the null hypothesis. So step 3 is pretty straightforward. You want to collect the data for your study and calculate the mean for your sample. The key here is to remember that you should do steps 1 and 2 before step 3. You want to set your hypotheses and your alpha level before running your study. This will ensure that you won't change your alpha level depending on your results. Because let's say your results are, let's say, 0.02, and you said alpha to be 0.01, you wouldn't be able to reject the null hypothesis. So if you collected the data and then set alpha, you could just change alpha to fit the data. So you'd say, alpha is going to be 0.05 now, and in that case, a p-value of 0.02 would still be significant. Whereas if it was 0.01, it wouldn't be significant. So always make sure that you set your hypotheses and you set alpha before collecting the data so that you won't be tempted to change those things based upon your results. So let's say we run our study and we find that the IQ for our sample is 135. Based upon this information, do we have enough evidence to be able to reject the null hypothesis? So in other words, is our sample mean far enough from the expected mean of 100 for us to be able to reject the null hypothesis? And it's really hard to tell because you just don't know if it's far enough from the sample mean, from the expected mean. And this is where step 4 comes in.